these examples, there's one thing that I'm sure you've noticed, that a lot of times you can just plug in the value that x is approaching into the function, and that's your limit. And that's because these functions that works for the most part, have been polynomials or rationals, and they're continuous there. We're going to talk about continuity in the next section, but they have no breaks in their graph, and you would have seen that concept before in pre-calculus. So if you have a polynomial function, you can just simply use direct substitution to find the limit. You don't have to justify every single step by using the sum and difference and constant multiple rules. And the same for rational functions if a is in the domain of the rational function. So in other words, if it's not a zero of the rational function, I can just plug in, or excuse me, the denominator of the rational function, I can just plug the value of a into the rational function. However, if x equals a is a zero, and there's a hole at x equals a, I can just substitute a into that simplified function after I cancel that common factor. We saw that in the previous example. So another tactic we use, if we have more exotic functions, if we don't have just a polynomial or a rational function, you also want to look at one-sided limits. So an example might be this function. It's not rational. I don't have any limit laws about absolute values or anything. So we need to define this as a piecewise function. So the absolute value of x over x equals positive 1 when x is greater than 0, and it's negative 1 when x is less than 0, and it's not defined at x equals 0. So when we look at the limit as x approaches 0 from the right, that would be 1, yet the limit as it approaches 0 from the left would be minus 1. So this limit does not exist. So this is just kind of summarizing the various techniques we've had for finding limits. The easy case is when it's a polynomial or a rational function and x equals a is in the domain. A couple more tools that we talk about in this section. Since limits are really just talking about the y values of functions on a graph, this rule is telling you that if all the y values of one function are less than all the y values of another function for some interval on the x-axis, then the limit of, in this case, g of x would be less than the limit of f of x. It just makes sense. So for example, when x equals 3, the limit as x approaches 3 of g of x is going to be less than the limit as x approaches 3 of f of x, because all the y values of f are greater than all the y values of g around x equals 3. However, if you look at x equals 1, that's not the case. On one side, g of x is greater than f of x, and on the other side, f of x is greater than g of x. So if you were going to look at that limit, you'd need to look at the one-sided limits. And that leads to a big deal theorem called the squeeze theorem. And that basically tells you if all the y values of a function, in this case g of x, are between the y values of two other functions, so in this case f of x, all the y values are greater than g's, and h of x, all the y values are less than g's. But if f and h both have a same limit as x approaches some value, then g must have that same limit. So looking at this example, g falls between f and h for all values. So the limit as x approaches pi of f and h is 0. Therefore, the limit as x approaches pi of g is also 0. That's called the squeeze theorem. G is squeezed between f and h. So here are some additional examples that show how you need to use preliminary algebra. So remember, given this problem, you can't just use the quotient law because the denominator has a limit of 0. But if you expand that numerator, you'll see that those 16s cancel and that you can cancel a common factor of h from the numerator and denominator. So then the denominator is no longer 0, and you can just evaluate that by direct substitution. Here's another example where you need to multiply the numerator and denominator by a conjugate. So what that does is introduces more terms into the denominator so that the denominator is not necessarily 0. So notice in this case, as x approaches 9, I can't just take the limit of that denominator. I can't use the quotient law because the limit of that denominator is 0. But if I multiply the numerator and denominator by the conjugate of the numerator, notice what happens is I get a common factor that cancels, and now this denominator does not have a limit of 0. So take a look at that a little bit more closely.